Okay, today we're going to review for exam 3. Before we do that, we'll go over to Math Breeze. Let's see if we have some announcements here. All right, here I wrote for the final exam. You should send in your worked out solution, send in your scrap. I'm just going backwards here. Tuesday, next week, Tuesday, I'll have an office hour during this class time. That'll be before the final. And Monday, we'll have a review for the final, also during the same class time on Blackboard. Okay, so tomorrow we have our exam. It's going to be available from 9 a.m. to 7 p.m. 70 minutes, no going backwards. All right. Okay, so let's go back. I have a review sheet online and videos, review videos. I put up a solution sheet to most of the review. All the answers are in the videos, but I also have most of the answers in the review sheet. Okay, so I'm going to do a different review, not the review on the review sheet, during class, so you can do the review sheet review and watch the videos. You can do that as well. All right, so here's the first question. It says, at most how many turning points and zeros does a polynomial of degree 10 have? All right, so just to remind you, let's say we have a polynomial, a graph like this. This would be a turning point, and this would be a turning point. Okay, and if this is the x-axis, then these are the zeros. So this one has 3 zeros and 2 turning points. Okay, this one looks like a typical degree 3 polynomial. Okay, so if you're ever wondering, what the answer to this question is, just, what a quadratic looks like. Okay, a quadratic is degree 2, and it looks like that. It has at most 2 zeros. Zeros, x-intercepts are the same, and it has 1 turning point. So it's 1 less than the degree for turning points, and the same as the degree for zeros. All right, so a polynomial of degree 10 has at most 10 zeros, same as the degree, and at most 1 less turning point, at most 9 turning points. Okay. If you have any questions, you can always, use the mic or use the chat to ask a question. Okay, so here we come to end behavior. Let's say we want to find an end behavior or something like this. So first of all, we have to determine what the first term is. So coming from here, we have x to the 4th. And coming from here, we have x. So that will be a total of x to the 5th. So the first term is minus 3x to the 5th plus other terms. Okay. The end behavior is determined by the first term. So the end behavior, we would write out like this. As x goes to infinity, minus 3x to the 5th. Okay, well, this is going to infinity, and we have this negative in front, so it's going to negative infinity. Okay. Now, as x goes to negative infinity, all right, let's look at minus 3x to the 5th. Okay, so now x is going to negative infinity. This is also going to negative infinity because of the odd exponent. So this is going to negative infinity, and this is negative, so the whole thing is going to positive infinity. Remember, when we have odd degree, the end behavior for a polynomial will be different on both sides. Even, it'll be the same on both sides. All right, here we have end behavior for a rational function. So we have to look at the highest order term on top divided by the highest order term on the bottom. All right, so let's say as x goes to infinity. So we're looking at minus 3x to the 5th over x squared Okay, that's minus 3x cubed. So as x goes to infinity, this is going to go to minus infinity because of minus 3. And as x goes to negative infinity, okay, we'll use this reduced quotient, okay? Minus 3x cubed is going to go to, this goes to negative infinity with the minus in front, it'll go to positive infinity. Again, this is odd, that's why it'll go to negative infinity. Okay, so let's go down. Here we want to find the zeros and their multiplicities. Okay, find the zeros. It's the same as finding the x-intercepts. Find where this polynomial is equal to 0. So just set it equal to 0 and solve. First thing we'll do is factor out x cubed. So we have x squared minus 4, and then factor again. So we have x cubed, x plus 2x minus 2. Okay, so we have, for zeros, we have x equal minus 2. And that would be multiplicity 1, because you have an exponent 1 here. And also x equal 2. Also multiplicity 1. Okay, and coming from this factor, we have the 0, x equals 0, and it has multiplicity 3. All right, because of this exponent 3. All right, so those are the zeros and the multiplicities. All right, let's look at another example. All right, let's say we want to find vertical asymptotes. All right, that would be for some rational function, something with a denominator. So vertical asymptotes occur where the denominator is 0. Okay, so vertical asymptotes, we would just factor this denominator. So this factors into x minus 7, x minus 3. If we can reduce, we do that. Now, there is no reducing here. Okay, so the vertical asymptotes will be x equals 7, x equals 3. Okay, so let me just put in parentheses, you will reduce first before you find vertical asymptotes, if there is some reducing to do. All right, let's see. Okay, let's say we have something like this. Okay, let's say we have, and we want to know, where is this positive? Okay, so we're going to do a plus minus analysis. Okay, so on the number line, we put the zeros. Okay, so we're going to put the zeros of this. So we'll put negative 5, okay, for the top here. And coming from the denominator, we'll put negative 3. And coming from the denominator, we'll put 2. And we just want to know, where is it positive, where is it negative? Okay, so plug in values. So if we plug in 3, for example, everything will be positive. So we have positive here. Okay, if we plug in, let's say 0, for example, in between in here and here, this is positive, this is positive, this is negative. So we have negative here. Here, let's plug in, let's say -4. That's in between. So this will be positive, this will be negative, and this will be negative, 2 negatives, so that will be positive. Let's say we plug in -6. This will be positive. This will be negative, and this will be negative, 2 negatives, so we have positive. So we want to know where is this positive, so it's going to be positive here. Okay, not, don't include the 0, we're just asking positive. All right, so we have, we can do x less than -5, x between -5 and -3, and x greater than 2. So that's where it's positive. Okay, so basically a plus-minus analysis. All right, let's say, if we have y equal to, let's say, x squared minus 4 over 3x plus 2. And here we just want to find x and y intercepts. Okay, so for the x-intercept, we set the numerator equal to 0. We want to know where is this equal to 0. It's 0 when the numerator is equal to 0. Or you could write, where is this 0? This is for the x-intercept. Okay, so when the fraction is reduced, it's 0 when the numerator is 0. Okay, so we have x equal -2, x equal 2. Those are x-intercepts. And for the y-intercept, just set x equal to 0, and we have -4 over 2. Or -2 for the y-intercept. Okay. All right, so we're going to exponents and logs. Let's do some of that. Or actually, let me do one of the earlier on problems. Let me see if I have that here. Sorry, am I recording? Yes, I'm recording. Let me turn my volume up. I didn't hear that so well. Let me just turn up my volume. Okay. Okay, there we go. All right. Okay, yeah, I wanted to do one of the earlier problems about polynomials. Okay, so we have, sorry, about quadratic functions. So let's say we have f of x equal 3x squared minus 12x plus 1. Okay, so let's say find vertex. Okay, so remember for the vertex, we have this little formula minus b over 2a. That's for the x value. So minus b, that would be minus 12 over 2 times 3. Okay, so we have 12 over 6, so 2. Okay, so that's the x coordinate for the vertex. Okay, so now for the y coordinate, we just substitute in 3 times 2 squared. That would be 3 times 4 minus 12 times 2 plus 1. All right, so we have 12 minus 24. Okay, so that's the y. Okay, so we have for the vertex, we have 2 comma minus 11. Okay, so we just have to remember this little formula, minus b over 2a. And another type of problem that we had in this section on quadratic functions was if a quadratic function has vertex, let's say minus 1, 2, and goes through, let's say 3, 4, find the function. Okay, so we write the function like this. Okay. A x minus h squared plus k, where hk is the vertex. So this is hk. Hk is here. So the first thing you do is just fill that in. So it will be x minus h, so minus minus 1. So here we have x plus 1. And k is 2. So we just have to figure out a, and we just substitute in this point. So we're going to put a 3 here and a 4 here. 4 for y and f of x, that's the same. So we have 4 is equal to a, and here we have 4 squared, that's 16, plus 2. Okay, just subtract 2. Okay, so divide, so a is 2 over 16. So that's 1/8. So then just finish this, and we have f of x is equal to, and here we have 1/8 in front, x plus 1 squared plus 2. Okay. So those are the two questions on quadratic functions that you might come across. All right, so now I think we can go on to exponent logs. All right, so we started with things like this, solving equations like this, let's say. And the way we solve this is put both in terms of a common base, if you can. Otherwise, we have to use logs, but that comes later. First, we put in terms of a common base, so these both can be expressed as base 3, in terms of base 3, because 9 is 3 squared, and 27 is 3 cubed. All right, and now just multiply over there, multiply the exponents. So here we have 2x plus 2. And here we have 3x plus 6. Okay, so now we're ready to match the exponents. Subtract 2x from both sides, and we have 2 is equal to x plus 6. And now finally, just subtract 6 from both sides, and we have x is minus 4. So that's how we solve exponent equations, when we can put both sides in terms of the same base. Okay, here's another early on problem. So I'm not going exactly in order here. Actually, no, I think this is from the previous test. I have one here where we're finding the inverse. Okay, these are from the previous test, so I'm going to cross this out. I think. Yeah, I think that's... Let me check the review sheet. I think finding the inverse was from the previous test. Let me just take a look. Yeah. Okay. I made up the test already, but I thought I might modify it if I found something that should be put on there. All right, I'll do one of finding the inverse. I'm not sure if I'll put it on the test line. It depends if it's in the... It's on the review sheet, but I wasn't sure if it's in the material for this test. I'm going to take a quick look. Okay, so let's go over to MathBreeze, and let me just take a quick look. So this test starts with 3.1. It starts right here. Yeah, so no, it's not on this test. So I won't include finding an inverse. Okay. So let's go back. Okay. All right. Okay, so let's continue with the exponent type equations. Just see. Okay, so we had something like this. Oops. One of those investment problems. Let's say if $500 is invested, at, let's say, 4%, compounded continuously. What is the value after 10 years? Okay, all right, so this is the formula that we use for continuously compounded. Okay, so we want to figure out what A is. P is the initial. The rate is 0.04. And the time is 10 years. So we have 500 times e to the 0.4. Okay. So we need, for this you need the calculator. All right, so I'm getting, just rounding this off. Okay, 746. Okay. All right. Okay, so now I think we'll start logs. All right, so let's say we want to, let me start with, I didn't do things in order here. So let's do this one first. Let's say we want to find the exact value of the following expressions. Something like this. It's a good idea to just set it equal to x and change to exponent form. So here we have base to the exponent, that's 2 to the x, is equal to 1 over 16. All right, and now we want to put both in terms of base 2. This is similar to one of the problems we did above. Let me just show you. That's similar really to this problem, what we're doing here. Here we put both sides in terms of base 3. Okay, so for these log problems, change to exponent form and put them in terms of the same base. So we can put 1 over 16 in terms of base 2. All right, so we have 2 to the x is 1 over 2 to the 4th, or 2 to the x is equal to 2 to the minus 4. Okay, so that means that x is equal to minus 4. All right, here, let's do another one. This is log base e ln. So this is ln e to the minus 5. Now these ln and e are inverses of one another, so we just get minus 5. They basically, you can think of them as canceling each other out. Okay, let's say we have log base 5 of 1 over the square root of 125. Okay, here we'll put this equal to x. So we have 5 to the x is equal to 1 over the square root of 5 cubed. So we're starting to put the right-hand side in terms of base 5. Okay, so 5 to the x is equal to 1 over 5 to the 3/2. That's if we write the square root as exponent 1/2 and then multiply the 3 times the 1/2. So we have this, and now just bring that up. That's 5 to the minus 3/2. Okay, so now we can just match the exponents. So x is equal to minus 3/2. Let's say we have something like this. All right, so here, the two ways you can do this. You can write this as e to a power. All right, so this is e squared, and this is e to the 1/2. We can just subtract those. Okay, 2 is equal to, in fraction form, 4 over 2, so this would be ln e to the 3/2. Now again, ln and e inverses, so we just get the 3/2. Or you could use log properties. Here's another way of doing this. We didn't introduce the log properties yet in this review, but we're going to do that soon. So you have ln e squared minus ln of the denominator. I'm going to write this as e to the 1/2, and then you can bring those exponents down. Now ln e is 1. That's, again, these are inverses, ln and e, and this is e to the 1. That ln e is 1, so we have 2 minus 1/2. Again, we're just doing 2 minus 1/2, which is 3/2. That's two ways of doing that problem. Okay, so we have those types of problems where you're figuring out the log of some value. Okay. All right. Let me just see what number I'm up to. Let's see, 13. Okay, let's say domain and range. First, let's say for y equal 2 to the x. So you should know what the basic graph looks like, and that will help you with the domain and the range. That's y equal 2 to the x. So the domain is everything. The graph goes all the way to the left and continues all the way slowly to the right. So the domain, anything can be substituted into this exponent, positive and negative. There are no restrictions. So here's the domain, and this is above the x-axis. So the range is y greater than 0. There's nothing below here. And let's do y equal log base 2. Again, you should know the basic graph. It's the reflection of this through the diagonal. Okay, so this is 0, 1. So this one goes through 1, 0. So anyway, the domain and range are going to be the reverse of this. The domain, everything is to the right, only on the positive side of the x-axis. So the domain is x greater than 0. And the range, this is going all the way down, and this is creeping up slowly, all the way up. So the range is between minus infinity and infinity. Okay. Okay, so here's some more log functions to solve. Okay, 2. Oh, I just did log base 2 of x. I could have done log base. I could have done y equal 3 to the x. 2 to the x is just, this is the question. Okay, the domain and range of this. That's the question. Okay, and here the question is, oh, you meant 1. Okay. How do we know? Oh, 1, 0 here and 0, 1. Okay, all the exponent functions go through 0, 1 because that's because 2 to the 0, anything to the 0 is 1. When you substitute in x equals 0, you get 1. Okay, now here the inverse flips around the x and y coordinates, so the inverse will go through 1, 0. All right, let me just write down log base 2 of 1 is equal to 0. For the same reason that we wrote up here. Put this in exponent form, and we have base to the exponent, 2 to the 0, is equal to 1. Okay, so that's why we have this. All right. Okay. All right, another type of equation to solve. All right, we're going to do this exactly the same way we did these problems up here. This one, we wrote 5 to the x equal this. So basically put it in exponent form. So change it to exponent form. Base to the exponent, 3 squared, is equal to this. And you see we just get a very simple equation. Like that. All right, so subtract 5 from both sides, and we have 2x equal 4. And divide by 2, and we have x equal 2. All right, let's do another one. Okay, so this is one type, and then we have this type, which is similar to number 14, except we have to first use log properties to contract. And we have a subtraction here. And this type, I'm just going to add, you must check. Okay, you can't substitute in a negative into a log function. So this can't be negative. This and this, okay, can't be negative or 0. Okay, so it can't be less than or equal to 0. It has to be positive. So if our x value makes either that negative or that negative, then we have no solution. All right, but start by contracting. We want one log function. That way we can flip over to an exponent function. So we contract, we make this on top. This is from log properties. Okay, so that's how we put these together. You know, if you expand, you'd have top minus bottom, right? Log base 2 of top minus log base 2 of bottom, which is what we have up here. So we're going in the opposite direction. We're contracting. So once we have one log, then we can change over to exponent form. Base to the exponent, 2 to the 1, is equal to this quotient. And this will be an easy equation to solve. Right, this is 2 over 1, and cross multiply, 2x plus 2, and multiply this way, 2x plus 1. Actually, I didn't mean to get the 2x on both sides. I don't want to do that. I'm going to change this problem. I'm going to make this a 3. All right, I'm going to change that. This is no solution, but I didn't want that to happen, so I'm going to change that to 3. I'll change it to 3 here. Here I'm changing them all to 3. Okay, subtract 2x from both sides, and we have 2x plus 2. Sorry, we have x plus 2. Okay, x plus 2 is equal to 1. Just subtract 2x plus 1 from both sides. Let me make sure I did that here. Yeah, I didn't. I changed everything to 3. Okay, subtract 2x from both sides, x plus 2 equal 1. And subtract 2 from both sides, x equal minus 1. Okay, and now we have to check. We just have to make sure that x equal minus 1 doesn't make this 0 or negative. And we see it does make this 0, x equal minus 1. Okay, x can't equal minus 1 because then x plus 1 would be equal to 0, and log base 2 of 0 doesn't exist. We need only positive in here, not 0, not negative. Okay, so no solution for this one. So you just have to make sure that these both come out to be positive. Otherwise, it's no solution. Okay, I have to cross multiply. Okay, yeah, it's 2x plus 2. You're right, thank you. All right, let me correct that. It is 2x plus 2. Okay, so I have to correct this whole thing. 2x plus 2. Okay, so we have x, here we have 2. Here we have x equals 0. Okay, and then we have to check. Okay, thank you. 0 plus 1, that's okay. And 0 plus 1, that's okay also. So, all right, thanks for that correction. Substituting x equals 0, that's no problem. This is 1. Substituting x equals 0, this is 1 again. So that's okay. Okay, yeah, substituting 0 here, we have 1. Let me just see one thing. These 2 of 1. Okay, let me substitute 0 into here. Something's wrong because something's wrong here. Let me look at this one more time. Okay, so this is what we have. All right, these can't be negative. We're contracting. We have a 1 over there. So we have 2 to the 1 equal this, 2 equal this, 2x plus 2. 2x plus 2 equal 3x plus 1. 3x plus 1. I'm sorry, I'm making mistakes. Yeah, 3x plus 1. The answer did not make sense because when you substituted in, both sides weren't equal. The check didn't work. So I'm redoing this with a 1 here. Okay, so we have x, this is a 1. Subtract 2x from both sides, x plus 1 equal 2. And then finally subtract 1 from both sides, and we have x equal 1. We'll check our answer to make sure this is correct. Okay, so let's go back to the original. We want to check x equal 1. Okay, so let's do a whole check, not just check if the individuals are positive. Okay, so we have log base 2, x equal 1, 3 plus 1, that's 4, minus log base 2. Okay, we have x equal 1, right? X equal 1, so here we have 2. Is that equal to 1? Okay, so I think it's okay. Right, x equal 1. So I substituted in here 3 plus 1, we have 4, and 1 plus 1, here we have 2. Log base 2 of 4, 4 is 2 squared, so this is a 2. Log base 2 of 2 is 1. Okay, so the answer does check. And these are both positive, so that's okay. All right, so sorry for the confusion, but now I think we have it right. Okay. All right, so yeah. Yeah, when the logs are subtracted, when you have 2 logs subtracted, you have to check. When in the previous example, this one, you don't have to check. It's just when the 2 logs are subtracted. That's where you have to check. Okay? Because you might get something negative when you substitute in. That's what can go wrong. That's the only thing that can go wrong, if something here is negative when you substitute in. Okay. All right, let's do some log properties. So for log properties, we have things like this, expand. Okay, so here's one. I'll use ln, but it could be log anything. And here, let's put w to the 7. And here I have square root z. Okay, so let's expand all at once. Remember, what's in the numerator gets added, and bring the exponents down at the same time. So that bring the exponent down, so we have 5 ln x. What's in the numerator gets added. Bring the 3 down, plus 3 ln y. And what's in the denominator gets subtracted, and bring the exponent down right away, minus 7 ln w. Here the exponent is 1/2. Bring it down, and it's minus because it's in the denominator, minus 1/2 ln z. So that's expanding. Okay, let's do one more where we have these x expressions. We did things like this. Let's say x cubed. Let's say square root x squared plus 1. Let's say x plus 5 to the 10th, something like this. So when we expand, okay, first we have ln x cubed, and bring the 3 down. So 3 ln x, plus for the numerator, bring down 1/2. And then subtract for the denominator, so minus 10 ln x plus 5. Okay, so that's the expanding using log properties, that type of problem. I think we did all the different types of problems. I'm just looking at what I wrote down and seeing if I left anything out. Just look at each problem. Okay, here, one more problem, just one more. Okay, yeah, one last problem. All right, here's the last one. Another continuously compounded interest problem. But this one, instead of solving for the amount for A, we're going to solve for either R or T, one of the exponents. If investment of, let's say, 1,000 grows to 2,000, in 5 years, and then it has to say compounded continuously to use our formula. Okay, find the rate. Okay, so we have, first write down A equal P, e to the RT, and then just start filling in. So we have $1,000 for P, and it grew to the amount $2,000. We want to figure out R, and the number of years is 5. All right, so divide by 1,000 first. Whenever we want to solve for something, a variable in an exponent, we log both sides. Okay, these are exponents. Log and e are exponents, so they basically cancel out. So here we have ln 2 divided ln 2 equal to 5r, and now just divide by 5. So r is equal to ln 2 divided by 5. Okay, we want to see the rate. Okay, so let's do that. So ln 2 is about 0.69. Okay. Okay, 1 second. Investment of $1,000 grows to $2,000 in 5 years, compounded continuously. 1,000, 2,000. I'm just looking this. Okay, what did I? Here we have to put for the rate. We have to use. Let me just. We have to use oh no, 5 years. That's 5 years. That's not. This is T, not the rate. Okay, this is T. 5 years. Okay, so I divided by 1,000 here, 2. Then ln both sides. Ln 2 is equal to 5r. And that's the rate. Oh, divide by 5. Okay, divide by 5. Okay, so that's it. Yeah, okay, thank you. Right, I knew it had to be a high percent. I divided by 2, which made the percent too low. Okay, so let me do that, ln 2. Okay. So it's about that. Okay. Okay, so we have 13.8%. Okay, I got 0.138. Or in percent, you'd have 13.8%. Okay. You could remember, like a lot of people remember, the rule that at 7%, your money doubles in 10 years. Okay. So here we're saying at 7%, your money doubles in 10 years. So here we're saying doubles in 5 years. So it has to be a lot more than 7%. In fact, it's double. It's double. That's the way it works. It's going to be, the rate has to be double the 7%. This is about 14% in order for the money to double in 5 years. Okay. So that's like a general rule that some people remember. Yeah, at 7%, your money doubles in 10 years. Okay, and so the way it works, if it's going to double in 5 years, then this has to double also. It doubles to 14%, about that. Okay. I think I did all the problems on the review. Let me just look again. Yeah, we did everything. Okay, you also have your review sheet, all right, and you should watch the videos. And let me mention, on the review sheet, I crossed out something. I crossed out number 7. Find the quotient and the remainder. In other words, it's just a division of polynomial problem. I wasn't positive if I did that in class or not, so I just crossed that off. I also crossed this one off. Some of them are crossed off on the review sheet, but I crossed off 2 more. Okay. So let me just mark off what you can see on the solutions, which ones were I crossed off some others. All right, so you can see I crossed off number 41. Here, I'll just write it down. 41 I crossed off from the review sheet. 42 and 43 were crossed off already. Okay, turns out 41, you could actually do that problem, but it can be done 2 ways, and it has 2 different answers. So one of the answers is correct, one is almost correct. So it's just, I just decided not to include that. And I crossed off number 47. I don't think I did one like that. We might have done it, but it's from a different chapter. All right. Yeah, let me just say one other that I crossed off, but you can see that in the solution sheet that I put up. I actually crossed them off on the solution sheet. Number 7 is that division, quotient and remainder. All right, and I don't think I did that. Yeah, go ahead. What's the question?
So the exam tomorrow is on the class time, or can I do it when I have the time?
When you have the time, it's going to be all after, most of the day. You'll look up on MathBreeze. I put the time range. Let me just see what I wrote on MathBreeze. I said starting at. Oh, okay. So I said starting at 9. Let me just see what I wrote here. 9 to 7. Okay. All right. So
when is the final?
Here, it's on here also. So the final is next week, 2 days. It's over 2 days. We have to do it during class time. So it'll be Wednesday. Let me just see where I wrote it. Here, right? Where did I write it? Here. Wednesday, June 10th, and Thursday, June 11th, during class time, 9:10 to 10:10 on Blackboard. And I'm asking you to send only for the final, not for tomorrow's test, but for the final, send in your scrap paper. Okay? So 2 days, but that one has to be done during class time because we don't want to have any conflicts. So that's what was decided, that everyone will do their final during their class time. Okay. Any other questions? All right. Okay, so keep studying what I did today. And also, if you came in late, this will be recorded. I'll put it up in the afternoon after I finish teaching. And do the review as well. Do this review and the review that's on MathBreeze. Do both, and then you should be fine. Okay? All right, so good luck tomorrow. Remember that Monday we're meeting again, okay? Regular class where we review for the final. And Tuesday we have an office hour during the regular class. Okay, you'll see all that on MathBreeze. Okay, so enjoy the rest of the day.